welcome back after the short break. We are discussing about the C amplifier, and then we are close to the small signal equivalent circuit. So, large signal analysis we have done, and based on the large signal analysis, what we said is the DC voltage here it is fixed. So, whenever we are going for small signal, first thing is that we will be considering this DC part is 0, and so we can say that this is AC ground. Of course, we do have this ground. Then next thing is that these capacitors are working as a short, and whatever the circuit we will be having, it is now that will be called the equivalent circuit. In addition to that, base to emitter, we are also having one VB on internal DC voltage, that also need to be made 0. So, base to emitter, what we have it is the R pi, we do have this R pi, and then we do have the signal coming here. So, we do have the signal directly coming here. Along with this R pi, of course, we do have RB, R capital B, and this is connected to AC ground, which means that this RB and this R pi, they are coming in parallel, and typically this resistance is very high compared to this one. So, we may ignore this part, we can simply consider this R pi. And on the other hand, at the collector side, so this is the base node, this is the collector side. At the collector side, we do have RC, which is connected to VCC, which is now AC ground. So, this is AC ground. I am using red color ground here just to indicate that this is valid for AC signal only. And then from collector to emitter, we do have the current, this IC current, but here again here it is having the DC part as well as the small signal part. So, we should say that DC part we are dropping it, and what we have it is only the small signal part IC. So, this IC equals to beta into IB, and the IB it is whatever the current it is flowing from the signal source into the base. So, this IB, if you see here this IB, it is this is Vs divided by R pi. So, this is what the IB. Now, that IB it is after multiplying with beta naught, it is giving us the small signal collector current. That current is flowing through this resistance, which is producing a voltage, and for it may be noted that the signal here, though it can go positive and negative, but for correct polarity and consistency of the input to output signal phases, we need to put a sign. Say for example, here whenever you are talking about base to emitter voltage, this is signal voltage, it can go plus and minus, but then we are putting plus sign here and minus sign here. Same thing for polarity of the IB. So, we are considering this is the positive direction of the base current. Likewise, whenever we do have the collector current, this is the positive direction of the collector current. With respect to that, if the collector current is flowing in this direction, the developed voltage here, it will be this will be minus and this is plus. So, the voltage coming at this point, it is minus RC multiplied by this IC. So, that is minus RC into beta naught into IB. Further to that, we can write this as minus RC beta naught into IB, it is Vs divided by R pi. So, that is what the V out. So, we can say that this V out expression is given here. So, this V out expression it is given here. So, from that I can say that V out, I should use this is small V out divided by V s equals to minus R c multiplied by beta naught divided by R pi. So, in fact, this is nothing but our voltage gain. In small signal model, if we map this equivalent circuit into voltage amplifier, small signal voltage amplifier, then this is representing us the voltage gain A V. So, we will see that again this A V, but its expression it is given here. Now, this small signal equivalent circuit, it may be having two ways of representing. The first one just now we are discussing. The other one it is again similar, only difference is that let me use a different color to consider that. This I c, instead of writing in terms of I b, let me use blue color. Yeah. So, instead of using I b, we can write I c equals to in fact we can write beta naught I b, it is V b e divided by R pi, right. And so, this V b e divided by R pi, this parameter, it is of course, it is a small signal parameter we already have discussed earlier. This is G m transconductance of the transistor multiplied by then this V b. So, this part it is basically the transconductance of the amplifier. So, in this red color what we have done is that this current we are writing in terms of I b, which means that this current source it is current dependent current source. On the other hand, if I use this model, then this is voltage dependent current source, right. So, this V b it is defining this the current, and then the remaining things however, it remains same, namely the output voltage here it is minus R c into I c, and instead of writing beta into I naught, now I can write this as minus R c into G m into V b e, and incidentally this V b e it is same as V s. So, we can write this as minus R c G m into V s. Again this is representing the same V out, and with this we can say that V out divided by V s equals to minus G m into R c. This is again the expression of the voltage gain if we are representing this whole circuit as equivalent voltage amplifier. So, I should say that this circuit we do have while we are mapping this circuit in the form of small signal equivalent circuit, there are, so this circuit whole circuit we are mapping in this form, and it is having two ways of writing this small signal I c here. One is in terms of G m V b, the other one it is beta times I b. Now, if we are mapping this circuit in the form of voltage amplifier, we prefer this expression over this one, that is because then input we are considering it is input signal we are considering as voltage rather than current. So, maybe in other model, while we are considering say the same CE amplifier as current gain current amplifier or maybe trans impedance amplifier, then we may use say the other model here. So, if I use a this current source as Gm into VB, whatever we will be getting, it is the equivalent, I should say that will be the input signal, it is the voltage. Now, if I consider this output as voltage, obviously then this current source along with this RC, we need to translate this circuit in the form of Thevenin equivalent. So, once we translate this into Thevenin equivalent model, then only we will be getting the output port as voltage source, and we need to map into this normal model, the known model, which is AV times V in, and in this case V in it is basically the VB, and then we do have the output resistance, and incidentally this output resistance and this output resistance, they are same. Okay. So, now if we map this small signal equivalent circuit into a voltage amplifier, what we are getting, it is the following. So, we are discussing about the this small signal model, and now if we translate this model in the form of voltage amplifier, what is the voltage amplifier we will be getting? It is voltage dependent voltage source at the output port, and then we do have the output resistance RO. So, voltage dependent voltage source, it is AV times the input port voltage. In this case V in, it is VB. So, this is plus and this is minus, this is connected to ground, and then at the input we do have the R pi. So, the input resistance is R pi of the transistor, and at the across this R pi we do have the VBE voltage. So, this is plus and this is minus, indicating if this is plus and this is minus, the corresponding voltage here, this should be in phase. However, we already have discussed that expression of this A, expression of the A, it is minus Gm into RC, or we also have said that in terms of current. So, for the time being, let us stick to this one, forget about this one, and then output resistance, it is same as the RC. So, this circuit, whatever the circuit we have discussed here, small signal equivalent circuit, we can map into this model, the voltage amplifier model, having these three important parameter: AV, output resistance, and then input resistance here. So, this is input resistance is R pi, and at the input, of course, we are giving the signal with a 0 voltage here, and at the output we are getting this signal. All right. So, that is about the how we are mapping the circuit into voltage amplifier. Note that this model, it is valid for low frequency as well as in the mid range frequency. However, if you go to higher and higher frequency, then this device may be having its own parasitic capacitances. From base to collector, it may be having one capacitance, and then base to collector, it is having another capacitance. So, base to collector capacitance, it is referred as C pi, and then we do have the C mu. These are essentially small signal capacitance associated with the BJT. So, if we are considering small signal equivalent circuit, and particularly in the high frequency range, then this capacitor and then this capacitor, they are again popping up, and we need to consider them. So, we need to consider this C pi and then C mu Okay. And then of course, we can consider their equivalent circuit here, which is having the C pi and then C mu. Note that C mu need to be connected to this point, not this point. Okay. So, in addition to that, I must say that so far we are ignoring the early voltage effect, namely the dependency of the collector current on the VCE we are ignoring, but in case if we want to consider whatever the dependency it is having, slight whatever positive slope in the active region, and this slope will be represented by finite conductance called G naught, which is defined as change in IC with respect to change in VCE. And this is called small signal reciprocal of small signal output resistance RO. So, if you consider this resistance or this finite slope, what you will be getting here, it is that one resistance here, which is either you can write in the form of conductance or resistance RO. And so, this resistance since it is coming in parallel with RC, as this is connected to ground, this is also connected to ground. So, the output resistance RO, it will be rather RC in parallel with small RO. So, this represents the complete model of the CE amplifier, small signal model of the CE amplifier, which is valid for low frequency as well as high frequency. And of course, in the low frequency regime, then this C pi and C mu, their effect it will be very negligible. And also this typically this R naught, it is quite high compared to RC. So, we may still consider this is RC, but once we replace this passive element by active element, which may be having output resistance comparable with this, and then we must have to consider this R naught. So, to avoid this so much of clumsy things, so let me go to the next slide, where I have the clear diagram of the small signal model. So, what we have, as I said, that in the small signal model we do have R pi and then RC, which is the output resistance, and so and so, and then we do have this resistance, this capacitance and this capacitance, they are getting added up. And also to take care of the early voltage effect, we do have R naught. So, this small signal model, it is referred as high frequency small signal equivalent circuit of the CE amplifier. So, this derivation we already have said, so nothing to discuss about that. And in case I must say one thing, I must add one thing, that this in case the source resistance is having signal source is having source resistance RS, then this voltage need not be same as this one. So, then we may have to consider this RS and then R pi to consider this voltage. And once you go to higher and higher frequency, this RS in combination with R pi and then C pi, also effect of C mu, you may call it as equivalent input capacitance. All of them are going to contribute to define the cutoff frequency of the amplifier. So, these capacitors are they will be playing important role to define the bandwidth of the circuit. So, whenever the situation comes, we will discuss that in detail. Now, let us see or let me highlight one issue of this this fixed bias CE amplifier is having, particularly the operating point, it is sensitive to beta of the transistor. So, then to let me use a different slide to discuss that point. sensitivity of operating point, as I said, sensitivity of operating point of the CE amplifier, particularly if it is fixed bias. So, if it is fixed bias, namely the IB, if it is decided by this RB and VB1 and VCC, then the collector current IC, which is beta times IB. So, as a result, if I fix this IB and then if I replace this transistor by another one having different value of this beta f, definitely the corresponding IC it will be getting changed. So, what will be the consequence? To explain that, let me go back to our previous method of finding operating point of the circuit. So, where we used to draw this IC versus VCE. So, we used to draw IC versus VCE characteristic curve for a given value of IB. So, IB it is fixed, and then also we used to draw the load line. So, we used to draw the load line defined by this RC and VCC. So, this node, this point it is VCC, and so these two together it was giving the operating point there. Now, typically we like to avoid, of course, this point as well as the saturation point, and whenever we used to give a signal here, we are adding the IB. As a result, this total IB, we are expecting that if the signal is present, then it will be going up and down like this one. And as a result, this the crossing point of the device characteristic and the load line, they used to it used to move from here to here, and as a result it was producing the output voltage. So, if this operating point is properly set, then if the in presence of IB, the IC maybe it is changing over this range, and this the meeting point, it was shifting from this point to this point, and as a result it was giving the output signal. And to get a very good swing, we want this operating point should be middle of this range. What is this range? Which is defined by upper side, it is defined by supply voltage VCC, and lower side it is defined by the limit of the active region, which is referred as VCE set, VCE set saturation. So, we like to keep this operating point middle, so that both the lower as well as the upper swing of the signal is to get a good one. Now, if you see that in case suppose we are fixing this RB, which is deciding this IB, and then if you replace this transistor having different beta. So, then what it would be happening is that this line for the same IB, because of different beta, it may be getting shifted here. So, this beta, if it is say beta f2 from beta f1, then the Q point now it is getting shifted from here to here, and if the Q point it is coming here, obviously the signal swing, if you see this side, it will be very much limited. This side it may be getting extended, but since this lower side it is getting limited, then if you apply the signal limit, it will be decided by the lower one out of these two limits. So, as a result, if the beta is getting changed from the previous value to this new one, the IC characteristic it is getting shifted here, and and then the operating point, since it is coming here, so that may create the signal and getting distorted towards the lower side. So, if you still continue giving the same amplitude signal for this operating point, so what we are expecting that then the corresponding output signal, let me draw here, it will be getting huge distortion, and this side it may be okay, like this. So, this distortion, of course, for analog circuit it is not acceptable. So, that creates the main problem. The change of this beta, it may be due to various reasons. In case if you want to replace this transistor by another one and you do not know the beta, then it may create problem. And to get the same value of the beta using which you have obtained this operating point may not be practically a good solution. The other problem, which is the typical problem, it is that this beta, it is a strong function of temperature. So, in case if the junction temperature of this BJT is increasing, this beta it may increase. As a result, this operating point it may be going up there, and that may affect the Q point, operating point of the circuit drastically, which is referred as thermal runaway problem. Why is it called runaway problem? If IC it is increasing due to increase of beta, maybe that is due to originally due to increase of temperature, and if the IC is increasing, then that may increase the power dissipation of in the junction, and that may further increase the temperature, and then that may lead to again increase the beta. As a result, it is having cumulative effect to increase the beta, and this Q point of the circuit it may go towards the saturation limit or active region limit. So, this problem can be, as I said, that this is a problem which is referred as the thermal runaway problem for CE amplifier, particularly if it is fixed bias. So, what is the solution for this is we can add a series resistor at the emitter. So, if you add one series resistor called RE, and then instead of fixing this current, probably we can try to fix the voltage here by different means, and then we can we will be seeing that the operating point will be having better stability. So, that gives us something called voltage bias with emitter degenerator. So, this RE it is referred as emitter degenerator, which desensitize the operating point of the circuit. But of course, we will be discussing that topic later, but since we are desensitizing the circuit by placing this RE, that will that also affect the gain of the circuit. Now, to get back the gain, we need to connect one bypass capacitor. So, this will be discussed in the next day, but just to give a hint that yes, CE amplifier with fixed bias, it is one good amplifier, but it is having this issue, need to be addressed differently, and we will see that how this node it will be biased in the form of voltage, namely by using a potential divider. Those things will be covered in the next class. So, what we have discussed today, let me summarize. We have started with simple operation of the CE amplifier, rather earlier whatever the knowledge we already have gathered, that we have discussed, and then we have discussed the biasing of the CE amplifier, namely how we define the operating point of the circuit by connecting a base resistor called fixed bias resistor RB at the base, and then we put a DC decoupling capacitor to feed the signal. So, in combination with RB and a capacitor C called coupling capacitor Cc to feed the signal, we obtain the appropriate arrangement of the circuit. And then we have analyzed the operating point little detail by considering the input port situation and then output port situation for large signal. And then we have discussed about the small signal equivalent circuit, and then we mapped that equivalent circuit into a voltage amplifier. At least as I said that typically CE amplifier it is considered as a voltage amplifier. So, that is what we have done, we have mapped into voltage amplifier. And then finally, we have discussed about the issue for which is existing for fixed bias CE amplifier, namely the operating point is sensitive to beta of the transistor, and that will be that need to be addressed by different means. So, that will be our next topic of our discussion. I think we are end of it. Thank you for listening.